Now we're going to look at example 2. In this one, we notice that there are 3 real zeros. We have a cubic, so we're going to have 3 factors, which makes sense, or we're going to have 3 zeros. And so what we do is look at those, and we see that 2 of them are kind of in between 2 numbers, and we can't really tell exactly where they are. As a matter of fact, I'm not even going to put dots there because that's kind of hard to see. But the third one sort of looks like it's a 4. And so my first task is to find one real zero. So I'm going to just check and see if this is a real zero. 2 ways I can do that. One thing is I could just put this into the equation. And I could say this is 4 cubed minus 2 times 4 squared minus 10 times 4 plus 8. And that would be 64 minus 32 minus 40 plus 8. And that does turn out to be 0. However, a faster, probably easier way mentally to do this would be to just use synthetic division. Because if 4 is a 0, I should get a remainder of 0 when I divide. So I'm going to put, or remember that this is considered synthetic substitution as well as synthetic division, that I can also figure out what I would get, what P of 4 is, by just looking at the last number here where the remainder would be. So once again, bring down the 1. 4 times 1 is 4. Then this would add this, so I get 2. Multiply 4 times 2, I get 8. Add, I get negative 2. 4 times negative 2 is negative 8. And when I add, I do get a remainder of 0. So this is also a check that this is a 0 of the function. So now I have divided my polynomial from a cubic into a quadratic, from an x cubed to an x squared. My first factor would be x minus 4, since my 0 is 4. My second factor is going to be x squared plus 2x minus 2 from the numbers that I obtained doing synthetic division. Now, looking at x squared minus 2x minus 2, or plus 2x minus 2, this will not factor. If it had factored nicely, I would have ended up with nice numbers as it crossed the x-axis here. So I'm going to have to use the quadratic formula again to find the result of x squared plus 2x minus 2 equals 0. So here I have a is 1, b is 2, and c is negative 2. Putting this into the quadratic formula, I have x equals negative 2 plus or minus the square root of 2 squared minus 4ac, 4 times 1 times negative 2, all over 2a. So this is negative 2 plus or minus the square root of 4 minus a negative 8. So that's 12, all over 2. Now be careful how you simplify this. And once again, I'm going to expect you to be able to do this, so watch carefully. Remember that the square root of 12 is the square root of 4 times the square root of 3. And the square root of 4 is 2, so I can simplify this as 2 the square root of 3. So I have negative 2 plus or minus 2 the square root of 3 all over 2. Now, do not just cross those out and say it's 2 the square root of 3 or negative 1 plus 2 the square root of 3. That is completely wrong. What you need to do is divide both terms in the numerator by the denominator, because this whole quantity is divided by 2. So each of these terms is divided by 2. So this is negative 2 over 2 plus or minus 2 the square root of 3 over 2, which is negative 1 plus or minus the square root of 3. So my zeros are 4, negative 1 plus the square root of 3, and negative 1 minus the square root of 3. Now I asked you at the top to verify that the real zeros are x-intercepts. So I need to verify that these two numbers are equivalent to these two x-intercepts. So if you were to do negative 1 plus the square root of 3, the square root of 3 is about 1.73. So this turns out to be about 0.73. And negative 1 minus 1.73 is negative 2.73. So if you look at the graph, this looks very reasonable that that would be 0.73 and that would be negative 2.73. So that verifies that those are the correct zeros. Now I'm going to go ahead and do example number 3 because it does not take very long, and then I'll do a separate video for example 4 because it's a little more difficult. Example 3 looks like it may be very difficult because there aren't any x-intercepts. If this were not factorable, I would not be able to find any of the zeros because I don't have anything to start with. But it turns out this is factorable. Hopefully you recognize that this is in quadratic form. We have a variable, x squared, and the square of that variable. So I can factor this as if it were a quadratic, like so. I can have this be x squared and this be x squared, and then I want to get 9 from my last term and 6x squared from my middle term. So if I do plus 3 and plus 3, this would give me x to the 4th plus 6 plus 3x squared plus another 3x squared and then plus 9. So to solve this, I have x squared plus 3 equals 0, or x squared plus 3 equals 0, which will clearly give me the same thing. X squared equals negative 3. I was jumping ahead of myself there. So x equals plus or minus the square root of negative 3, which is plus or minus the square root of 3 times I. That happens twice. So basically I have 2 double imaginary zeros. My zeros are positive the square root of 3i, positive the square root of 3i, negative the square root of 3i, negative the square root of 3i. Make sure that I is outside the radical. I didn't really have to put the positive signs, but those are my 4 zeros. So if you wanted to write this in terms of its linear factors, I could actually write this as x minus the square root of 3i, x minus the square root of 3i, x plus the square root of 3i, x plus the square root of 3i. These are known as its linear factors. These are what are known as its irreducible quadratic factors. In other words, I can't really reduce these anymore by factoring. I can solve them, but I can't factor them anymore. So these are known as irreducible factors. And I think if you look I think I'd talk about that a little bit more on the last page of one of the worksheet keys. Okay, now we'll stop and do example 4 as a separate video.